Today we'll do a deep dive on vectors in CockroachDB, looking specifically at L2 or Euclidean distance, cosine, and negative inner product, and why you might want to use each of them for different use cases. The first of these scenarios will use the L2 or Euclidean distance, and this is simply the distance between vectors, and it's useful for clustering, especially when all vectors are comparable. In this demo, I'll present the user with a color wheel and I'll allow them to drag their mouse around the color wheel, and I'll use their current hover position on that color wheel to derive similar colors that they might like based on their current selection. And because the data is normalized, i.e. RGB vector is naturally quite normalized, L2 is a perfect fit. I'm looking for perceptual closeness or geometric intuition that you would see if you were to look at a color wheel. And color spaces tend to lend themselves nicely to Euclidean distance. What's interesting here is that magnitude is taken into consideration. So for example, unlike cosine distance, which would treat light blue and navy blue as very closely related, L2 won't. There'll be two distinct colors. So lighter blues will be clustered closer than light blues and dark blues. And negative inner product would so strongly favor the magnitude that everything would be strongly matched to white. I'll show you what I mean. First, I'll create a table called color, into which I'll have an ID, a name, and a vector, which represents the RGB value. Next, I'll insert 1000 evenly spaced RGB values into that table, and I'll run my application. Now, I already have this running, and it looks like this. So this is my color wheel. You'll notice that as I drag my cursor around the screen, I'm suggesting colors that are similar to the one I have selected. And this is running at 60 frames a second, and 60 times per second, I'll be making a request to CockroachDB to get these colors that you see on the left-hand side. Let's take a look at that in the browser. So over here in the metrics, I'll look for the last 10 minutes, and you'll see that I spiked at just under 40 requests per second, and that was our requests to the database to get those colors. Now we'll take a look at cosine distance, and we'll go from a 3-dimensional cluster to one with hundreds. Cosine compares the angle between vectors, making it useful for comparing text embeddings, where semantic meaning is more important than magnitude. In this scenario, I generate embeddings for animal names, and I allow the user to input an animal and compare it against other animals based on their semantic closeness. Cosine is a good fit for this because it ignores content length. The words cat and elephant, we as humans know are semantically very different, but we know that they're semantically different, not necessarily just because their names are very different in size and content. And it matches on meaning, so dog and puppy will have very similar embedding values. So if I search for dog, I should find puppy and vice versa. Let's create a table and I'll show you what I mean. I'll create a table called animal, which will have an ID, a name, and a vector. The 384 dimensions here are reflective of the text embedding model that I'm using. And I'm using Ollama for this, so it's all running locally on my machine. I've tried a bunch of different text embeddings, and because of the small size of this, I think it's only around 64 megabytes in size. You'll see that some of these matches are a little bit funky. First, I'll generate the embeddings, and you'll see that we'll go through all of the animals in a random data set, and we're embedding them and storing them in the database. Next, I'll run my application, which allows me to search for values. So I've got a drop down here. Let's expand that a little bit. So I've got a list box here. It's not very easy to see, but I will display the matches up here. So let's look for jellyfish. And these are the matches that CockroachDB is returning that closely resemble what I've searched for based on their cosine distance. So we found goldfish, fish, crab, shark, and dolphin. All pretty good matches. Let's try dinosaur. So we found lizard, frog, alligator, crocodile, and turtle. Of the animals that I have, only 140, these are pretty sensible matches. Let's try cat. We found tiger, leopard, both big cats. Dog, I guess there is a similarity there because cats and dogs. Lion, again a big cat. And hound, a dog. And finally, I'd be remiss if I missed cockroach. We found mosquito, spider, locust, frog, and grasshopper. Now let's add puppy to that list of animals. I've just embedded puppy, and now if I search for dog, I do find puppy. I also find prairie dog, which semantically isn't very similar to dog, but this is probably reflective of the fact that my model size is so small. Conversely, if I search for puppy, I should find dog. And again, I find prairie dog, but dog is our closest match. Finally, we'll take a look at negative inner product. In this scenario, I've written an application that allows a user to record audio, which gets embedded and stored in CockroachDB, and then record another piece of audio to search against. Negative inner product is particularly suited for this type of use case because it works with unit normalized vectors. So it's like cosine, but it's faster. And this is because it only performs a multiplication and an addition. There's no square root calculations like in L2, and there's no division calculations like in Cosine. And depending on the audio encoder you use, the magnitude can also be driven by the audio clarity. So higher quality audio might result in higher quality matches. Let's create a table and you'll see what I mean. I create a table called voice. I have an ID, a transcription of the text, the file name that's storing the audio, the vector itself. I'm using OpenAI for this, and they use 1536 dimensions, and I create an index. Next, I'll run my server, which serves as a backend to a front-end application, and I'll run my front end. Now, this is actually already running, and it's over here. This is my voice detectorizer, and I'll record some audio, which will be stored in CockroachDB, and then we'll perform some searches against it. The rain in Spain falls mainly on the plains. I'll store that, and that's successfully stored. I'll do another one. Peter Piper picked a peck of pickled pepper. And I've Googled some tongue twisters, so you can watch me suffer now. Crouching cautiously, calm and collected, curious crickets. How can a clam cram in a clean cream can? We'll store that one. If two witches were watching two watches, which witch would watch which watch? That one's disgusting. Now let's do another witch one. It's nearly Halloween, so I'll watch South Park's Sons of Witches episode. And I'll do one more witch-related one, so I can look for the word witch in my embeddings and also rank them in terms of their proximity. I'll also watch the witch film, which I tend to call the V-Vitch, given how its name is stylized. So those values are stored in CockroachDB. 7 rows for 7 audio clips, and now I'll perform a search. Where does most of Spain's rain fall? If I search the database, we found one close match, which is our recording with the transcription, the rain in Spain falls mainly on the plains. I'll do another one. Let's look for witches this time. Which witch watches which watch? Our tongue twister comes out first with the highest match. Then we return the witch film and then the Sons of Witches South Park episode. If you've taken nothing from this video, I hope you were at least able to laugh at my horrifying attempts at tongue twisters. But hopefully today's demo has given you a fairly compelling idea as to which vector algorithms to use for which use cases, and how easy it is to integrate CockroachDB into your AI workflows. Everything here was stored in CockroachDB and harnessing CockroachDB's natively distributed C-SPAN index.